result of matter density calculation and photon density calculation here, and finally give a summary. As we know that the lambda CDM model with the cosmological constant is the simplest model to describe the dark energy model, the dark energy phenomena. And we also know that this kind of model fit to current observations very well. But there exists several theoretical problems, such as the hierarchy and the coincidence problems. There are many attempts to solve these problems, and one of the simplest way is the running cosmological constant model, in which the cosmological constant is intended to be time dependent. So if we start from the Einstein equation, we can use this form, and the cosmological constant lambda here is time dependent. There are many running cosmological constant models in the market. The quadratic model may come from the quantum effect induced by cosmological renormalization group, and the linear model may originate from the 2CD vacuum condensation, and several people are working on such kind of mixed model. And there are many literature mentioned that the quadratic model can perfectly fit with the observational data, and they got a smaller chi-square compared to that of the lambda CDM case. And in this work, we concentrate on the second one, the linear model. Considering the FRW metric with the perfect fluid, we can write down the Friedmann equations written in this form. Here, rho and the P are the energy density and the pressure for radiation and matter, corresponding to the relativistic and the non-relativistic particle. And the lambda, this term is the effective energy density and the pressure for dark energy. If we really go back to the Einstein equation and consider this term to be the effective energy moment tensor of dark energy, we can estimate that the pressure of the dark energy is equal to minus energy density. So this means that if we define the equation of state for dark energy defined by the pressure over energy density, it should be -1. And the equation of state for the radiation and the matter are 1/3 and the 0 respectively. In addition, from the conservation equation, we can obtain this relation. And as I mentioned in previous slide, the equation of state of dark energy is equal to -1. So the red part will equal to 0. And then we can observe that the dark energy density is a function of is time dependent. So it must be non-zero. So we cannot decompose this equation into two independent equations with the dark energy and the matter separated. So the matter and the radiation avoid the body, but couples to matter and the radiation. So we can write down these two equations. And here, Qm and the Qr are the coupling between the matter radiation to the dark energy. So we can write down in this form. Here, Ci is an arbitrary constant we introduced to control the coupling between dark energy and matter and the radiation. So in this work, we will concentrate on this kind of model. In the no linear model, we don't have this term. This term is 0. We don't have this term. And the cosmological constant, the dark energy, or say the cosmological constant, couples to the baryon only. And in that case, there must be a lot of baryons created by the dark energy decay. So, but we do not observe this kind of phenomena. So, in this work, we phenomenologically extend this model and make the cosmological constant or the dark energy coupled to the matter and the radiation. And we introduce the one additional cosmological constant term here. Then we can rewrite the energy density to be this form. If the observational data prefers, let me talk about this first. Rho lambda 0, this is the energy density of dark energy in present time. And the lambda 0 plus lambda 1 is equal to unity, and the lambda 1 can be defined in this way. We relate lambda 1 to sigma, and the H0, this is the Hubble parameter at present time. If the observational data prefers lambda 0 equal to 1, then the cosmological constant model is preferred. And if the observational data prefers lambda 1 close to 1, then the linear running cosmological constant model is preferred. So then I want to discuss about the switching parameter Ci. So in general, we can consider 3 cases. The first one is that the dark energy couples or decays to matter and the radiation simultaneously. And in second case, the dark energy only decays to matter. And in third case, the dark energy only decays to radiation. In this plot, we can see the evolution of energy density. The longitudinal axis is the energy density for matter radiation. Matter is the blue line, radiation is the green line, and the dark energy is the red line. And the horizon axis is the E40 of the scale factor. So we know that the current time is n equal to 0 here. The solid line is the case of lambda 0 equal to unity, or says the lambda CDM limit. And the dotted line corresponds to lambda 0 is equal to 0, and the lambda 1 is unity. So this is purely the linear running cosmological constant model. So we can observe that in this kind of scenario, the dark energy decays to matter and the radiation in both the early and the late time of the universe. But the radiation and the matter creation is relevantly small compared to the background matter and the radiation energy density. But in the late time or in the future, the evolution of matter and the radiation deviates from that in the lambda CDM case. And on the other hand, we can also observe that no matter what lambda 0 and the lambda 1 is, such kind of model can have daytime daytime dark dominated era. So in this case, we can say that this kind of model can describe the daytime oscillating phenomena. So in case B, when the dark energy only decays to matter, we can get a similar result, but the radiation follows 10 to the -4 powers decrease. But if we consider the dark energy only couples to radiation, we can find that in present time, we have to observe a lot of radiation at present time. So this case must be excluded in our discussion. We only focus on the case A and the case B. So before we go to the perturbation equation, let me show the energy density of matter and the radiation normalized by the lambda CDM case in the early and the late time. And we can find that if lambda 0 is equal to 0, then almost 60% of the particles are created in the daytime of the universe. Okay. Let me go to the perturbation table. And in order to calculate the perturbation result, linear perturbation result, we use the CAN and the cosmology program, to open source program to calculate the evolution of density perturbation. And we choose the synchronous gauge in K-space. Then, from the conservation equation, we can derive this equation. As we can image that, here we consider the cosmological constant is homogeneous and isotropic. So we can image that when the particle created from the dark energy K homogeneously and isotropically, then the density fluctuation should be suppressed. So there is one additional term here, the suppression term. So yes,
it shows the synchronous gauge here.
Yes.
When you choose another gauge, the result
the same. We also got the suppression term, and with the very similar form. Yeah. So we plot the matter Hall spectrum, which is proportional to the matter density perturbation. And the black line corresponds to lambda 0 equal to unity, is the lambda CDM case. And the cyan line corresponds to the purely linear case. So we can see that when the lambda 1 becomes larger, then the deviation or suppression from the lambda CDM model much. So this phenomena also occurs in the case B. So we can estimate that the large number of lambda 1 should be, the model parameter lambda 1 should be constrained in this model. And this phenomena occurs in photon Hall spectrum. When the lambda 1 becomes larger, then the deviation becomes larger. So by using the cosmology program, we fit the model with the observational data, including the Planck data and the large scale structure observation and the frequency observation. This is our result. Red contour corresponding to case A, blue contour corresponding to case B, and we cannot see the number here, so I just this table here. And the model parameter is constrained to be less than 0.1 in this model. And another value which is interesting is this one. We find that the best fit of chi-squared for the running cosmological constant model is greater than the lambda CDM case. So we can make a conclusion that this model will not give us a better result compared to lambda CDM case. So this is my summary. The lambda CDM, the running cosmological constant model is suitable to describe the daytime oscillating phenomena at the background level. But when we investigate the linear perturbation level, the matter pulse spectrum and the photon pulse spectrum will strongly constrain the model parameter lambda 1, and the constraint is at this order. Okay, thank you.
Any questions? What's the most significant reason why the sum of the mass is smaller than the lambda region?
You say the neutrino mass? Oh, okay, thank you. We include the matter pulse spectrum data, and then the massive neutrino will also suppress this kind of data, the matter pulse spectrum. So in this case, if this model suppress and the massive neutrino suppress again, then they will deviate from the data further. So yeah.